Hi friends, welcome back to my channel. This is Turner. So in video 1.1, we formalized set in this file, which talk about unions, intersection, the De Morgan's law, and all of that. Now we pick up the same turn-length file and try to finish section 1.2 of the book. So the full source is in the link of the description if you want to follow along completely. So same workflow as 1.1. So we open the textbooks and we try to mark down the bolded terms as we go to find out which terms is worth formalizing. So we follow the book's order and we're going to skip all of the examples like the matrices, like the n-dimensional real spaces, or anything with calculus, because that's in another book. So the book starts with the Cartesian product. So it is defined as A times B, and it is an order set. So it's defined as A times B, which is a set of ordered pairs. So we're gonna pick one element from B and pair them up. So in turn length, so that is modeled as the structure, Cartesian product. And you notice that there is a new syntax here, the for statement here. And this is basically creating a variable length of input to this structure. So this lists the factor set A1 through AN. And we can use the annotation syntax to render them as a chain of A1 times A2 times AI times all the way to AN in mathematics, and it is rendered in a pretty good way. And so for the cases where we only take two sets to form a Cartesian product, namely A and B, we can just use one array here, A, comma B, to fit in this Cartesian product structure. So the same structure, but just n equals 2. The book dimension are cubed as an example of A to the power of n. So this basically means there's n dimension crossing each others, and you can have a pair of n numbers. So real numbers are their own formalization. So we'll do that in an analysis book, which in another video series. So please hit the like button if you want to see that series. So this is how we model Cartesian products. And next we have relations. And think of a bag of ordered pairs. So each pair picks something from A and something from B. And the book says that this is a subset of A times B. So it means relations is just a selected pairs of all of the possible pairs that you can form from A and B. So in turn, a relation itself is a set, just like textbooks. And the subset law inside says that the members of self must already be a pair so every member in self must be a pair in the Cartesian product in A and B. So the law is really a membership rule, so nothing outside A times B can sneak in this relation structure. So now a function is not a separate species. It is a relation that behaves like a machine. So you fit in A, you get exactly one B back. And the pair of small a and small b is in this relation. So Turner puts the uniqueness checks on relation as the well-defined properties. So a function is literally just a relation which is well-defined. So instead of writing pairs by hand, we write f bracket a. So this is the apply method when you plug in a specific element, a from the domain, and returns a b. And the book shows a classical counterexamples, which is not a function. And this is what not well-defined means in plain language, which means one input, but there are multiple outputs. The mapping is not unique. So our well-defined properties formalize exactly that. So for each A exists a unique B with the pair of A and B exactly in the relation. Next, the book defines onto, one-to-one, and bijective maps. These are well-known properties a function can have. So in turn, this lives in the property blocks on functions, and they are annotated just like adjectives because they are indeed adjectives, and even though they are predicate applied on the function, they should be displayed as an adjective. And to use them, you have to put it in the bracket right before the function type in application. So this is how we can attach to a function. Okay, so if you look at its properties one by one. So for surjective, it means that for every B in the range, there is some A maps to it. That means every element in B has something to map from it. So it is fully mapped, okay? If you look at the turn length syntax, it says that for all B in the range, there exists an A in the domain such that when you plug in A, we'll get B. So every B exists an A in B. So this makes sense. And next we have injectivity. So which means different inputs will give you different output. So if you look at the Turing examples, it says that if for A1 and A2 in the domain, if they are not the same, then the result of applying them is also not the same. So if you have two elements that are the same in the range, should the domain's element be mapped to them separately? I mean, that's a separate mapping. Okay, so if A2 are equal separate elements and B1, B2 are also equal, they're mapping to a different element. So it sounds like it's not a mapping to a unique element, but because B1 and B2 are the same, so they are essentially still mapping to the same element. Duplicate element count in injectivity. So if you look at this definition in Turing, we say that A1 not equal to apply A2. But there's also a famous statement saying that apply A1 equals apply A2 will imply A1 equal A2. This statement is actually equivalent to this logically when you try to use the contrapositive theorem in pure logic. So this is fine. And next we have bijectives. And it's interesting because this is just a convenient definition to bundle the surjective and injective definition together. So what we're going to do is just put a round bracket here. And notice that this is the same syntax when we try to apply multiple properties preceding a type, preceding a structure like this. So we can put in as much property as we want before a type when we try to instantiate a structure. So this is handy. Okay, so next we have a law specifying what a function should satisfy. So here we say that the apply A must be in the range. So whenever you plug in something in the domain, you should always get something that is within the range. And you cannot map outside the range. So this is a defining law of how the function application should work. And it is about a method inside the function structure. So it's important to know that a law should be a relation concerning everything inside the structure. It can be concerning about self, the structure itself, the generics, or the methods, the fields, or the interconnection between them. Next is composition of functions. So if we take f from A to B, and then g from B to C, and when we try to compose them using this notation syntax, so you can see from this notation that f is closer to the input than g. So that's applied first and then g. So that's why this is reverse order. So f composed of g is that applying f first, then apply g. So you can see that if f is from A to B, g is from B to C, then this whole mapping range will fall into a pipeline that cannot escape from A to C. So remember this. So remember the function. So remember the laws of functions. So when we apply f first, the variable input cannot escape B, and then when we apply g, the returning variable cannot C. So eventually, it is a pipeline from A to C only. So in Turing modeling, composition is still a function, so it inherits the applied method from function implicitly. The books insert some maps. So the books later use some examples of linear maps, permutation, and polynomial composition, and these are very high-level algebraic structures, so which we will talk about later. So what comes next is a theorems on composition. So it's talking about the associativity of composition. So the order of applying does not matter because they eventually just return to the same pipeline from the source domain of the very first function to the range of the very last function. And then we have the property of how composition preserve the injectivity, surjectivity, and bijectivity properties of the component functions. So in Turing, we model this big composite theorem using only one theorem block, and there are 4 leaf nodes. So and we can name names. So here we just name that as associative, injective, surjective, bijectives. Each has its own proof block, and there's no way we can merge them. And there's no benefit of merging them because they are separate properties that can be true independently. So the same pattern that we see in the basic set theorem that we, in video 1.1, where we group around theorems in one theorem blocks. Okay, so next we have identity function, which is rendered as id subscript with s, which is the domain of the function. So an identity function basically maps something from the domain to the range, and the domain and range are the same in this case. And then we have this inverse function, which relies on the existence of an identity function. So an identity function may also operate on an empty set. It would just map, because there's nothing to pass to the apply method, there will be no output. So we can never whether a return type is not in the empty set, because you cannot return anything from an empty set to it. This application will never be working because the premise will not be true. You cannot have something in the domain. You cannot find A in domain. So I guess this is a trivial case. So accepting it or not makes no difference right now. So the book defines an inverse function as a structure that relies on a function. So let's look clearly. So identity function is sends s to itself. It's inheriting from function because it is a function, after all. And then we have inverse function. This is also a structure that takes in a function and it becomes another function. And you can see that the inverse function relies on the identity function, such that the function composing with the inverse function becomes identity function, because the function from A to B and then composing the function from B to A is eventually channeling the variables from A back to A from this loop. And the law defining an identity function is such that whenever you apply, remember the apply method comes from the inheritance of the function. When you apply something in the set, in the domain set, you always return the same thing back to you in the same set. But for inverse function, the law says that whenever you compose a function with its inverse, whether from the left or from the right, they will always give you an identity function. Well, depending on the order, you give your identity function in the domain or identity function in the range. Okay, so that's really handy. So that means inverse is basically canceling out the function. But there's one very tricky notation here, the concept of invertibility. So we're talking about invertibility function. So when we say a function is invertible, we mean that there exists such an invertible function. We are saying that it exists such an inverse function. And this property clearly lives inside a function and this invertibility property is a property on the function. So this is away from the inverse function properties. So here we have really a definition that's splitted in two structures. So one is an inverse function, another is a property inside function. And if you look at this property clearly, you can see that the statement simply put exists inverse function that is of self. So what does this mean? So exist used to be existential quantifiers, but here Turnlang puts more guarantees and guardrails to make sure this is right. So by saying there exists a type like this, notice there's no variable name for this. We simply state that there exists an instantiation of this structure. And what this means is that when we pass the self inside inverse function, we must satisfy the law of the inverse function. So we are turning a law into something that we need to prove. Here we are trying to make an axiom into a theorem. Because it makes sense. If you claim something and you do not provide any evidence on why it exists, and whether there is no logical flaw or not, you cannot firmly say that this thing exists. And this draws bigger problem in formal mathematics, is that we often just give conditions to a structure and we hope that it is consistent. But sometimes it is not. Sometimes we will have laws that are conflicting each other. And we don't know about that when we try to define this structure. Because we will have to derive contradictions when we're trying to prove something about this structure. When we try to apply the laws from the structure in a proof, only then we will insert those conditions into the context and try to find itself. But tactics are the only source of the only mechanism to check whether something is consistent. whether there is no contradiction or not. The proof checkers can never, check your condition in a general case. So this is very important to keep in mind, and I'll make a separate video about this in the series of pitfalls of formal methods. The formal method is not perfect. So next theorem in the book, a map is invertible if and only if it is an injective one. We are not going to go through this. So the proof of this is not finished yet. I'll make a separate video about this. Okay, so that's everything about functions. We are going to really something really interesting. And this is where the things started to get abstract because we're trying to use set to define equivalence, which is a weaker kind of equalities. And mathematicians have many levels of equivalences, and they're named differently to establish relationships so that we can move forward in developing pure mathematics. So now we're going into equivalence relations and partitions. So in the same file, the new topics. So relations, this is different than the relation block in Ternlang as a syntax. This is a relation as a concept. So relation on one set is not a map from two sets, it's a map within one set, but it's different than identity function because identity function always return the same element, but a relation does not. So this is what makes it different than a function. So remember, this is a relation. It is not a function, so it's not well defined. So we'll follow the book again. So the book defined so on X. And it gives us some properties, and these is exactly the same properties that equality will have. So reflexivity just means that one element is always equivalent with itself. So being equivalent means in the equivalent relation. So that is the mindset we need to turn around. And then symmetric means that if x is equivalent to y, then y is equivalent to x. So left hand side, right hand side is interchangeable. And then we have transitive. So when you say x is equal to y and y is equal to z, then x is equal to z. Okay, this is very intuitive. And all of these are within one law block because they share the same context, x, y, and z. So I just make them put it in one proposition with a block statement that you can name an individual part, which means they are true simultaneously. And it's very handy to call them. You just call basic dot reflexive or basic dot symmetric when you try to apply the law. Okay, and then we have some equivalent fractions, their derivatives, and mod constant circles in R2 space. These are very good motivation of why we want to develop equivalence relation, because it's basically saying different thing in this set could be equal. Okay, they could somehow be so that is really. So imagine a circle in outer space. So it is a relation again, which is a subset of Cartesian products. It is a pair. It is all possible pairs of the points on the circle. So whenever 2 points are on the circle, you put it in a pairs. You can be guaranteed that this pair is in the equivalent relation as a relation. And we have congruence model and but we'll do that in two where we define integers. Okay, next we have our final concept, partitioned and equivalent classes. So a partition of X is a family of non-empty subset. A family just means a set, okay? A set of X that are pairwise disjoint. So that means all of the set within this set are not overlapping with the other set. They contain completely distinct elements from each other. So which means that you are cutting the cake without them sharing same pieces. I mean, which is very intuitive. So Ternlang model partition first, the container says that each cell C is non-empty, otherwise it will be trivial, and it is a subset of X. Then it introduces two laws on them. So one is disjoint, which means there's no intersection, and second is the covering. So that means a big union of all of this partition set will have to reproduce the original set. So right after defines the equivalent classes of X. So it is a structure that takes a single element from the big X and all y's with y related to x. So in Ternlang, we model it as an equivalent class with a law of called depth. which is with a defining says that for all of the y in the big X, if y is equivalent to x, that means y will be in this equivalent class. So basically, equivalent class is a set of all of the equivalent members to an element x in this big set. So we gather all of the equivalent members to x within this one set. Lastly, we have a law saying that the equivalent class is a subset of big X. Okay, because it gather element only from X, so it must be a subset from X. Okay, after this definition, we have a small lemma in the file saying that the members of an equivalent class lies in X. So those are handy. And these three concepts, equivalent relation, partition, and equivalent classes, are close together, as we will see in this final theorem. It says that the equivalent class of X form a partition of X. Using a particular, this is really powerful. It means that we can divide a set just by grouping equivalence things together. And then this set that we have will be separate from each other, and they are going to cover the whole set. And this is a powerful statement for all sets. As long as we can have an equivalent relation on X, we are going to group them together. We are going to group any set by a similar element. This will be really important in later chapters when we try to do some exhaustive analysis on a set. So if you have a proof, just look at the says that there exists such a thing. So what does this mean? So in the textbook, it simply says the equivalent classes, so all of the equivalent classes form a partition of X. What does formed mean? So it's basically saying we can instantiate a partition of X using only the equivalent classes of X. So partition have this guarantee of covering the whole set of X. And equivalent classes just means that I'm the ingredient that you're going to use to form the partition. I mean, I am the partition, the set of set. I'm this family of sets that you can use to fill out all of the X. So this is a really powerful statement, and we're going to look at it carefully. So one thing you notice is that the proof consists of only one giantetics. And that final statement is an existential statement, which again, it's possible to construct a structure with this certain input. And when we have this, and in order to prove this theorem, we are going to provide, and we are going to turn every axioms inside partition into a proposition that we're going to prove, into a sub-goal that we try to prove. So there are actually 4 sub-goals related to partitions. Namely, so if you look at partition structure carefully, so we have this C1 means the assumption attached to C. So the first assumption, which is C is not empty set, and second is the subset of C to the big X. Okay, so once we have two laws, one is the cover, one is the disjoint. So it all comes from the original structure. There's no secret origin. And to be careful of this partition structure, we see that inside the square bracket, which is the container mark for this structure, we're saying that a partition is a container, which is a set, because it's a set, and the element type inside this partition, inside the first level set, is another set satisfying these two these two assumptions. And here I'll just lay them down very nicely because, and you can see that the assumption to a generic and the laws are in the same, are treated, they are not nested. They don't have a dependent type of relation. The relation of C1 and C2 comes first. Law of disjoint and cover comes later, but they're essentially parallel properties, and they're parallel and separate properties that you need to satisfy. So Turner is really handy for managing your assumption wherever you want, because you can put your assumptions closer to the variable declaration instead of scattering them around. And you can see that if a theorem looks too complicated, involving too much things, especially involving self and some generic like X, better to put it in the law, because it's not good to put it as assumption for C because it is too much. We have x here, but it's totally fine because it's mainly about a relation from c to x, and this is intuitively put. People may have different taste on how to manage these properties, but here it's fine to describe it because the text box mentions c is a subset of x right after c, and these two things are separate sentences. So this is really handy when trying to introduce variables. So that, and after all, you can see that this proof is really detailed compared to the textbooks because textbooks just misses so much things. Okay, so this is conclude section. In the next video, we're going to look at some reading question from the same chapters and gonna look at some other proofs more carefully. So please hit the like button and subscribe, and let's make mathematics intuitive.